All right, so we know about continuity of a function at a point and then at an interval. We know what to look for discontinuities. What about some further properties? Or in other words, what are we, if we combine two functions or if we multiply a function by a number, when do we still have continuity? Well, it's pretty nice. Basically, we're saying that, all right, just let k be a real number, and then f and g are continuous at x equals a. So they're continuous functions at a. If we know that, then the following are also continuous at x equals a. All right, if you take f, a continuous function, and multiply it by any scalar, any number, this is called a scalar multiple, or constant multiple, that's also continuous. If you take the sum or difference of two continuous functions, still continuous. If you take the product of two continuous functions, still continuous. You take the quotient, it's still continuous if g of a is not 0, okay? So we said g was continuous at x equals a, but now because it's in the denominator, we need a little more than that. We need also that it's not equal to 0, because that would keep the whole fraction from being undefined as long as it's not 0. Okay? And then any rational power. Any rational power is still continuous if it's defined there, okay, as long as we're not taking, negative numbers and trying to do an even root of them. Okay, so that's all good news. Furthermore, we know that a very important way of combining functions is putting one into the other. So a composite function. So if you remember a composite function, so say f composed with g of x is f of g of x. Okay? So what happens if we take one continuous function and put it into another? Well, we have a more formal statement here that says if g is continuous at a and f is continuous at g of a, then the composite function f of g of x, also expressed as f of g of x, is continuous at a. So basically, as long as the chain of continuity holds, then everything is fine. So we can casually say a continuous function of a continuous function is a continuous function, but we have to be a little careful there. And I'll show you with these examples. So imagine you did sine of e to the x. This is sine of e to the x, not sine x times e to the x. Sine of e to the x. Okay, so we've basically taken e to the x and put it inside the sine function. All right, so we don't have a lot to worry about here because e to the x is continuous everywhere. Because it's defined everywhere, and it's one of those functions wherever it's defined, it's continuous. And sine of x is continuous everywhere because, again, it's defined everywhere, and it's one of those functions that is continuous everywhere it's defined. So that means that sine of e to the x is continuous everywhere. When we say that, we mean on the real line. Okay, great. Now, let's look at the next one. Well, we've got 1 over something, over e to the x minus 1. All right? So basically, we've taken g of x. This is like considering g of x to be e to the x minus 1, and then f of x to then be take 1 over that. Okay, so that's really the individual functions. And the idea is that g of x here, is continuous everywhere. okay? But f of x is not continuous when x equals 0 here. But that is the whole denominator here. So 1 over e to the x minus 1 is not continuous when e to the x minus 1 equals 0. Or in other words, e to the x equals 1. And that would mean, well, still x equals 0. Okay? So that's why it ends up not being continuous at x equals 0. All right, because when I put 0 into the denominator, all right, I get 1 minus 0. I get 0 from the denominator, and hence I get a discontinuity in this function. Okay. Now, it can be a lot less clear sometimes if you are starting with the individual functions. All right, so let's take a deeper look at a different one. Maybe it'll be clearer. So if we have, if we want to look at f of g of x, and we have an f of x as 1 over x minus 6 and g of x as x squared plus 5, now, we could put them together and take a look at the discontinuities, or we could do it sequentially. So basically, I'm saying that, all right, let's look at g of x, which is x squared plus 5. That's continuous everywhere. All right. F of x, which is 1 over x minus 6, is not continuous at x equals 6 only. Okay, but that's not the point that where the composite is not continuous, because basically I have to figure out what I would put into g to get this, which then goes in to f and then would give me a problem. Essentially, I don't want to put 6 into f, so I can't get 6 out of g. Now, when would g of x equal 6? X squared plus 5 equals 6. X squared is 1. X is plus or minus 1. So for the composite function, x can't be plus or minus 1, because that would give a problem. That would give not a problem with x squared plus 5. That would give 6, which would then give the problem here in that f would then be 0. I mean, I have a 0 in the denominator. So that's a problem. Okay? So as long, what I was saying about the chain of the composite, as long as points are allowed to go into one function, come out and go into the next function, then we can keep our continuity.